Thanks again, Sanjin, for the introduction. Good morning, everyone. I'm going to talk about the main topic of my PhD work today, integrated design of floating wind turbines. I am doing my PhD under the supervision of Professor Alessandro Croce in the Aerospace Department of Politecnico di Milano. The outline of today's presentation is going to start with the project background, and I will motivate the topic of my PhD. And I will explain briefly the design framework for floating wind turbines that we have developed in the past years. And in detail, I'll briefly talk about the simulation coupling and the optimization problem that we use to run a design study. And we will see some preliminary results of a sizing experiment of a substructure for a floating wind turbine. Now we'll finish with the conclusion and outlook. So I would like to start with a comparison of CapEx breakdown between floating wind turbines and the other design counterparts, in particular the onshore wind turbine and the fixed bottom offshore. As you can see, the turbine share of the CapEx has been decreasing as we move to the floating wind turbine case from 70% to 34% and then to 24%. So this, on one hand, brings a lot of challenges in terms of design because there is high level of multidisciplinarity, but on the other hand, it also promises a lot of potential to drive down the cost of energy more efficiently if we can manage to model the interactions between these subsystems and run an integrated design. So the related work of my study was the multidisciplinary design optimization problem tool that we have developed in our department in the past years. So the idea is to integrate the floating wind turbine into this design optimization tool so that we can design certifiable floating wind turbines considering all the challenges of the floating wind environment. So in order to run the design case, we need to run time simulations. And how do we do that? We have developed a simulation coupling environment. And on one side, we have the CP Lambda, the hydroelastic solver, which calculates finite element simulation, time simulation. So everything above the sea level is calculated in CP Lambda. And on the other side, the hydrodynamic model is implemented in a reduced form of FAST. So we have broke down FAST into a reduced form of in a dynamic link library. So we use hydrodyne and Murdyne routines and wrap them in a different script in a dynamic link library so that we can consider different load sources into one platform reference point, which then used in a controller interface to communicate between the CP Lambda model and the FAST model. And we implement this by actuators and the sensors. So the CP Lambda model will calculate the deflections at the tower base, and these deflections are used in the FAST routines to calculate the hydrodynamic forces, and these forces will be fed back to the CP Lambda model. And this is the general scheme of the structural optimization that we are aiming at. So we will have the parameters here of the substructures and the turbine. And once we perturb these parameters, we can go into the input generation of each aspect, so hydrodynamic aspect on top and the turbine system on the bottom. And in this presentation, for the sake of simplicity, we are going to fix the turbine parameters, and we will only look at the platform parameters. And more in detail, how do we do this platform parameterization? We start with the platform geometry. We do the mesh of the floating platform, and then we put this geometric mesh into humps, which is a WAMIT equivalent open source frequency domain preprocessor. And once we run the humps, we get the hydrodynamic matrices and displaced volume of water, obviously, which are required inputs in hydrodyne. And once we have defined the displaced volume of water, we inherently calculate the total mass of the system. And as I said, if we fix the turbine mass, then we effectively find the platform mass by subtracting the turbine mass from the total mass. And once we have the platform mass, we need to do some intermediate steps by using the geometry, the cross-sectional area, which we keep constant in this case. So we are ignoring the stiffened plates within the spar platform, so the wall thickness is kept constant. And we have some intermediate steps to find the steel mass and ballast mass, necessary ballast height. The rigid body will be defined with all this information in CP lambda, so the platform itself is defined as a rigid body, and all we need to define is the platform mass, center of gravity, and the inertia matrix. So with all set, we have the hydrodyne and CP lambda inputs, and we are ready for the load calculation. So I would like to also start talking about the preliminary sizing of substructures based on ultimate limit states. This is the case study that I have that we have run for this presentation. We have used the NRL 5 megawatt turbine on top of OC3 Hive and Spar platform. Here you can see that we have used 7 design variables, 3 from the platform side, the total draft of the spar, the radius of the main column, the thickness of the spar wall, and on the right hand side we see the parameterization of the mooring lines. We have fairlead attachment height, the diameter of the mooring lines, the radius of the mooring layouts, and the portion, the non-dimensional portion of the mooring line that is lying on the seabed in the steady state. And we have incorporated several design constraints. To begin with, the global limit states, we have maximum values on mean platform pitch, maximum platform pitch, and maximum and mean heave. The platform offset is set to, the maximum platform offset is set to 10% of the sea depth to prevent breakage of the power cable, and the maximum anchor uplifting angle is set to 5 degrees. And we also incorporated the dynamics constraints. So the lowest platform natural period needs to be above 25 seconds to prevent the resonance condition with the excitation, wave excitation. And in order to ensure the Matthew stability, we have opted to put the ratio between the natural frequency of pitch to heave in a certain window that you can see here. And lastly, we have also incorporated the ultimate loads constraints, which we have defined looking at mostly the DMV standards. We have the characteristic mooring line tension, which needs to be below the minimum breaking load of the mooring line. We have buckling constraints on the shell elements, and also we are considering the column buckling. And on top of that, we have a maximum nacelle acceleration constraint as well. And to define all of these constraints, we have used these references, especially these first two papers are very relevant for this kind of study. And the environmental conditions we have used, as I said before, I have used the ultimate limit states as design drivers. So we are running extreme conditions for each design candidate, and these are the extreme conditions that we are simulating. These are taken from the 50-year return period for Norwegian Sea. As you can see in this table, the values for significant wave height, the hub height, velocity, and mean wave period. The turbulence is defined as a standard IEC turbulence model, and we have employed a vertical shear with an exponent of 0.14. And the current wind speed is also estimated by using an equation from the DNV standards, which is given for an offshore site again in Norwegian Sea. And we have some cost and material assumptions. Here you can see that we have defined some simplified cost elements to get a simplified overview of the platform costs. We use these values for the steel cost. The ballast material is kept as concrete with density of 2,000 kilogram per cubic meter. The mooring lines used are studdless chains with a price equivalent to the steel cost, and the anchors are sized by the maximum anchor load we have found in the simulations. So we use this equation here, which is taken from a product catalog to calculate the maximum holding capacity of the anchor, which will define the mass of the anchors and then subsequently the cost of it. And the mooring lines properties are defined with these two equations that are listed here. And here we can see the optimized design, which is a result of the optimization function fmincon, which is a gradient-based optimization function in MATLAB. And we used total cost of the substructure as a merit figure. So we are trying to minimize the total cost of everything you see here. Here you can see the baseline values and the optimized values here on the lower row. Here we can see a drastic change in the draft of the spar, whereas we had to widen the column of the spar. The thickness of the spar went backwards to drive the cost down, and this is one of the important outcome of this design study. So the mooring diameter needs to be increased in order to increase the axial stiffness of the mooring lines, so that we have less mooring line tension violence, let's say. And so the fairlead attachment point is, for example, is moved upwards according to the change in the draft of the spar. So here we can have a look at the constraints to make a more efficient comparison between the designs. So here you see the constraint utilization factors. One means it uses all the allowable constraints, and above one means the solution is not feasible. As you can see, the baseline design was not complying with the constraints that we have defined. And in the optimized design, we can see that we ensure that we have a feasible design for all the constraints, especially for the mooring line tensions, so fairlead tensions that you see here, and the maximum platform offset is moved to the feasible region. We have less column buckling due to shorter draft and less shell buckling due to wider platform diameter, because we increased the cross-sectional area, so the stresses are decreased. So another point to mention is here that the power is equal for both designs. This means, so this is a practical constraint that we have put so that we can do a fair comparison between two designs. So they are generating the same power output in average from the EC2 case, which is above rated extreme condition but power production. And we tried to get these values into feasible region, and we needed to pay the price by sacrificing some of the stability of the platform. As you can see here, the maximum pitch and the average pitch is increased compared to the baseline case. And another negative outcome is that we have higher ultimate loads at the tower base that you can see here. So here we can have a look at the simulation of a time series that is coming from the EC3. So here, no power production, the turbine is parked in a storm condition. The simulation includes the turbine system itself. Here we are only visualizing the hydrodynamic parts. Here the scale is a bit big to distinguish the differences between the designs, but you can see that the magenta line, the magenta design, the baseline design is always a bit downstream compared to the optimized design. And we are looking at the vertical plane, as you can imagine. So this is a projected line. All the mooring lines is actually have the same blade, have the same length, just 120 degrees apart. We can move on to the design comparison in the aspect of materials and costs. Here on this table, we can clearly see that the cost reduction is coming by decreasing the platform steel massively. So 20% decrease was possible. So we needed to compensate with higher ballast, of course, just 5% more concrete mass. And as we saw from the constraint comparison, we needed to increase the diameter of the mooring lines. So we have a huge increase, relative increase in the mooring lines mass, and also anchors. We have an increase, which means that we have higher loads at the anchors. And in total, we have a 3.3% reduction in the total system. So we have shown that we can do a preliminary sizing for the substructures. What can we do with this? I would like to also take this opportunity to advertise a bit the other work that we have worked on. So this wind farm design tool that we have developed also in collaboration with Craig, previous presenter. Here you can see that we have an integrated wind farm design that we can find an optimum site and an optimum layout for this site synergistically. So as an example, if we take this site, which is a result from a constraint of 35 kilometers from distance to shore, and if we plot the 10-year ERA 5 data for 10-meter height wind speed versus significant wave height, and here you can see the correlation between the significant wave height and the mean period of waves. Here it is obvious that we are going to simulate different environmental conditions, so we can update our extreme environmental conditions after optimizing our wind farm design. And also, if we find a layout description, we can update our constraints. For example, we can put a maximum value on our mooring line radius. And we can also investigate more the impact of offshore environment on the blade design. Here we can have a look at the comparison of blade root flat piece moments. So we can see the differences between the extreme cases without the waves and with extreme waves. So there is a 60% increase in ultimate loads, as you can see here. And obviously, this will also provoke an increase in pitch actuator duty cycles due to the motion of the rotor. And to conclude, we have shown the potential of the integrated design to reduce the LCOE. We have seen that the coupled effects require longer time simulations to be resolved. That's why this design procedure takes a bit of a long time. And the mooring line loads and platform offset are decisive constraints for the design. And the limits to the platform displacement, so these maximum pitch, maximum of horizontal offset of the platform, they are going to have a huge impact on the costs. And the future work can be done on a prior wind farm design study, so that we can help defining our system design constraints. We will further investigate the effects of optimized design on the blade loads, and a full aerostructural rotor design for this presented system will follow in the future. And these are the references that I used for this presentation. And if you have any questions, I'd be happy to answer them. Thanks for your time.
Thank you, KUTAY.
Thank you.
So, are there any questions in the room? Yes.
Thanks, KUTAY, for your presentation. Very nice. I may have a question regarding the methodology that you use. So you optimize the platform based on extreme events,
Yes.
mainly. If you would consider the whole set of load conditions that you have, like within 20 years of operation, does your design in the end would account for that, or like do you expect your design to resist to all the loads that will encounter a floating turbine over 20 years? Is it consistent to that, or would you need to implement that in your method in order to also account for them?
Yes, thanks. Yes, definitely I would need to incorporate this. But if, as I showed in the first slides, the platform is modeled as a rigid body. So the fatigue calculation that we can do can only come from the tower side. So once we start optimizing the design of the tower and the rotor, we can build everything based on fatigue. So we can account for all the load cases that will happen within these 20 years of lifetime. Once we optimize the tower design, we can put the same constraints to the spar platform. But on the other side, the current model cannot calculate the platform's flexibility, so we don't have any information on the loads along the spar. We only have the loads at the reference point, which means we can design everything on this point. So we can design the tower, and the thickness of the tower, the diameter of the tower will define the rest of the structure in the spar below the sea level. Yeah.
Okay, another question?
Yes.
Thank you for your presentation. I have a question on your results you show when you compare your initial configuration, your optimized configuration with several in the diagram. I think it was around slide 14 or 13, something like that. My question is about my understanding on your conclusion, on your results. If I look at this diagram, I understand that the optimized configuration is very sensitive to pitch motion, max pitch motion. So
yes.
The constraint that you put on pitch motion is important in your to find your optimized configuration. You didn't write that in your conclusion, but you wrote that is the offset and the mooring load maybe the constraint, the most important constraint for your optimized configuration. So my question is, why is not in your conclusion the fact that the pitch motion, the constraint pitch motion is very important for this design? And the question is, if you perform some sensitivity analysis of the max pitch motion allowed for your process of optimization, I think it could be interesting to perform this kind of sensitivity analysis of the max pitch motion allowed for your design.
Yes, definitely. In the results, so in the conclusions and outlook, my last conclusion point was that the platform displacement constraints have huge impact on the cost. So actually, I was thinking to use this platform displacement as an umbrella term for pitch, heave, and all degrees of freedoms. So yeah, I fully agree. So it is also in my conclusions. And on the other side, it's definitely a good idea to run a sensitivity analysis. For example, in this case, the maximum pitch that the baseline was giving was 3.94 degrees, and what I get with the optimized is 5, so exactly the constraint. Yeah. So it's just 1 degree difference, but it makes a lot of difference in in the material saving. Yes.
I think you can increase this value, especially I think the maximum. You put 10 degrees,
Yeah.
probably you can increase this value. Maybe your optimized configuration is very sensitive to this parameter. If you put 12 or 13, I don't know,
Yes.
maybe you have a lot of gain in your cost.
Yes, yes, definitely. The entire design takes a very long time, so like 2 days more or less. That's why we are in the this development is more or less recent development. So we are in the phase of exploring the potential of this tool at the moment. So yeah, it's a very good idea. We can also explore this, definitely. Thanks.
Okay, thank you, KUTAY.
Sorry.
We will stop here
Okay.
to stay in the schedule.
Thanks.